So if you recall where we left off last time, we were talking about the reduction of um, of aldehydes and ketones because that reduction will give alcohol. All right. And so we talked about the first method already, and this was through the catalytic hydrogenation of aldehydes and ketones to give primary and secondary alcohol. Now, this mechanism was exactly the same as we saw for catalytic hydrogenation of alkenes and alkynes. All right. Um, so you have the metal catalyst. Um, in this case, the double bond is not obviously a CC double bond, but rather a CO double bond. But mechanistically, it's the same in that the hydrogen that is adsorbed onto the surface of the metal will add a hydrogen to each of the double bonded atoms. And so in this case, as you can see here in this generic example, the carbon of the CO double bond got an H, and then so did the oxygen of the CO double bond, and that results in an alcohol. All right. So that is one way of doing this. As I mentioned last time, the only real difference here from the catalytic hydrogenation of the alkenes and alkynes is in the metal catalyst. These bonds are harder to reduce, and so a more active catalyst is typically used, and that one that's most often used is called Raney nickel. All right. Okay, so let's go ahead and look at the other way of reducing these. And this is actually probably the more common way of reducing aldehydes and ketones. And this is through what's called a hydride reduction. So when we talk about hydride, hydride is technically just hydrogen with 2 electrons and thus is negatively charged. All right. Now, there are a couple of reagents that are most commonly used in order to deliver hydride. And we're going to focus on two of them. The first one is called sodium borohydride. And actually, I'm not going to write it out. It's right here. Sodium borohydride. And the second one is lithium aluminum hydride. Now, you can see the formula for sodium borohydride down below. What that really looks like is you have a sodium ion, and then you have the BH4 minus ion. The second one is a very similar reagent. It is that's the lithium aluminum hydride. And it looks very similar. Just this time the positive ion is lithium, and you have the AlH4 as the negative hydride source. All right. Now, these will effectively do pretty much the same thing. Like I said, they are both sources of hydride. However, there are some key differences. So sodium borohydride is much weaker. And thus more selective. You are only going to be able to reduce aldehydes and ketones. That's it. LAH is a much, much stronger reducing agent. LAH is so strong, LAH will effectively reduce anything with a carbonyl. So yes, that includes aldehydes and ketones, but that also includes things like esters, carboxylic acids, amides, nitrile. Acid anhydride, acid halides. It is what I usually call a sledgehammer of a reducing agent. All right. So I want to go ahead and show you one more distinction with this. Sodium borohydride is relatively weak. We'll go ahead and kind of show you a simplified mechanism here. Again, we kind of just think of these two reagents as a source of H minus. And so if you add this to an aldehyde, the H minus will attack the carbonyl. That's going to result in this alkoxide intermediate, this O minus intermediate. And generally, sodium borohydride reductions are run in either methanol or ethanol. And the point of that is that it provides a proton source, right? That O minus species can just reach over and grab a proton from the protic solvent. And in the end, when you reduce the aldehyde, you end up with a primary alcohol. Now, the sodium borohydride, or sorry, the lithium aluminum hydride, like I said, is much, much more reactive. So notice the difference here. Oh, by the way, very, very commonly, in fact, most often, people will simply abbreviate lithium aluminum hydride as LAH. Notice the distinction here between the two reactions. With the borohydride, we're using a protic solvent to dissolve everything. With LAH, I'm using ether. In fact, you cannot use a protic solvent with LAH. It will catch on fire. In fact, the only major lab incident that I've ever been involved with was as a result of an LAH reduction. You have to keep it away from any kind of a proton source, any kind of moisture, even moisture in the air. If LAH sees the ambient environment, it will catch on fire. And so you do have to be quite careful when working with it. But again, mechanistically, it's pretty much the same. So you can think of LAH as H minus. And again, it's just going to come in and attack the carbonyl, generate an alkoxide. The only difference here now is that I don't have a protic solvent that I can go and protonate the O minus with. So much like the Grignard reactions, remember how in the Grignard reactions, we always had a step 2 H plus. You're going to do that with the LAH as well. I need to, at some point, give that some acid so it can protonate and I can isolate a neutral organic molecule. So in the next step, we will acidify, and then we can protonate the alkoxide. And so you can see in this case, we reduced the ketone, and that provides the secondary alcohol. No, that depends on what you're reducing. If you reduce either one, if you reduce an aldehyde with either one, you get a primary alcohol. If you reduce a ketone with either one, you get a secondary alcohol. All right. Questions there? So let's look at some examples. Oh, actually, before we do, I mentioned a second ago, LAH can be used to reduce a lot of other things as well. So I want to show you just a couple examples of that. So this is LAH reducing a carboxylic acid, and then LAH reducing an ester. And I'll kind of take you on a little baby mechanism of this just to kind of show you what happens. If you take an ester, for instance, and you reduce it with LAH, again, you can think of that as just a source of H minus. It would come in and attack the carbonyl just like it did in the previous example. Only in this case, once you make that intermediate, we have a group that could potentially leave, right? And so what happens is we actually reform the carbonyl and kick out that leaving group. And that generates the aldehyde. Now, as you just saw in the previous example, there is no way you can isolate an aldehyde in the presence of LAH. LAH reduces aldehydes very, very easily. And so this happens one more time. H minus will add to this. And at this point, there really is no possible leaving group. So this thing will just hang around until at which point you acidify the solution. And then you protonate the alkoxide. Mm-hmm. Yes, it does. So the bottom line is you can get primary alcohols from the reduction of aldehydes, from carboxylic acids, and from esters. They all reduce to give primary alcohol. All right, so now let's look at some examples here. So we're starting to mix things up a little. We've got some multifunctional molecules here. So I want you to think about what the product of this, of reducing the compound, this test compound with sodium borohydride, and compare it to the product of reducing the same thing with LAH. So the questions here are fairly straightforward. Is borohydride capable of reducing a ketone? What do you say here? Can only reduce aldehydes and ketones. All right. So yes, borohydride will reduce the ketone and it will reduce to the secondary alcohol. Can borohydride reduce a carboxylic acid? No. Remember, it can only reduce aldehydes and ketones. So that carboxylic acid is going to remain untouched. So that would be your product. We reduce the ketone and leave the carboxylic acid alone. Do you see the difference that we're going to get if we use the stronger lithium aluminum hydride? Now, LAH will certainly reduce a ketone. I mean, if borohydride can do it, the LAH certainly can do it. So we're still going to reduce the ketone to the secondary alcohol. The difference is LAH is such a strong reducing agent, it will also reduce the carboxylic acid. And that carboxylic acid gets reduced to the corresponding primary alcohol. Any questions on this one? What about this one? You can give me the product of that. So can borohydride reduce the aldehyde? Certainly it can. So that is going to reduce to the primary alcohol. Can sodium borohydride reduce an alkene? No. Remember when we introduced this reagent, I told you that it is only good for aldehydes and ketones. So no, it is not going to touch the alkene, so that alkene remains just as it was. All right, questions there? Okay, so this, you might find this useful as just kind of a reference. This has listed all of the reducing methods that we've talked about up to this point and what they can and can't reduce. So as you get more practice with this, it'll become more second nature to you, but you might find this helpful as you kind of start getting used to this. It has all of the reducing agents in one place. Okay. Now, before we move on, try your hand at this one. So here we have three potential things that could possibly reduce. Now, by the way, we just said borohydride cannot reduce an alkene. So that kind of takes care of one of those. Can borohydride reduce a benzene? No. Benzene is much, much harder to remember. You can hydrogenate an alkene. You cannot hydrogenate a benzene. The benzene is much, much harder to reduce than regular double bonds. So if borohydride can't reduce a regular alkene, there's no way in heck it's going to be able to reduce a benzene. So all the double bonds in this molecule, well, all the CC double bonds in this molecule are going to remain as is. The only thing that can reduce here would be the aldehyde. All right. Questions on that? All right, let's go in the opposite direction. We're going to talk about oxidation now. So what we've been doing was kind of looking at the carboxylic acid reducing to the aldehyde going to the alcohol, or the ketone to the alcohol. Now we're going to go in the other direction. You can start with alcohols and oxidize up to the carbonyl, and if it's a primary, up to the carboxylic acid. Okay, so I'm going to introduce these oxidizing agents as strong and weak. All right, most of the ones that we're going to talk about in this class are going to be strong oxidizing agents. And the strong oxidizing agents are typically some form of a heavy metal, either a chromium or a manganese. All right, so you can see a few of the strong oxidizing agents here. They tend to be some form of chromium, like a chromic acid. That chromic acid, that H2CrO4, can also be formed by taking chromium trioxide and mixing it with consulfuric acid. That also makes chromic acid. You can also see these dichromate salts mixed with sulfuric acid. All right, so a lot of these chromium-6 species are strong oxidizing agents. Another one that is very, very common is potassium permanganate. That is also a strong oxidizing agent. By the way, this chromium trioxide sulfuric acid up here is oftentimes called the Jones reagent. So you might see that too. You might just see on arrow Jones reagent. Even bleach can act as a strong oxidizing agent. Now, this isn't like the bleach you pick up at Target. It's a little bit stronger than that, but it's still sodium hypochlorite. The only one that I'm going to introduce to you now that is what I would consider a weak oxidizing agent is this reagent here, pyridinium chlorochromate. And pyridinium chlorochromate looks like this. Now, by the way, I'm never going to ask you for the structure of pyridinium chlorochromate, but sometimes all these terms and acronyms and stuff like that just make it seem like alphabet soup. So they do have structures behind them. But many times, most often, people, instead of saying pyridinium chlorochromate or writing pyridinium chlorochromate, they'll just abbreviate it as PCC. Now, the distinction, I've kind of introduced all of these oxidizing agents as strong or weak. The difference is how they treat primary alcohol. So have a look at this first example. Can you recognize this as a primary alcohol? Right, there's my carbonyl, and that carbonyl is bonded to one additional carbon. So this is a primary alcohol. When you have a strong oxidizing agent, which we've got potassium permanganate on the arrow, which is one of our strong, I mean, the way I would remember these to make it easier for you, there is only one weak oxidizing agent at this point, and that is PCC. So if it is anything other than PCC, it's one of the strong ones. All right. So what's going to happen when you do this oxidation is this primary alcohol will oxidize first to the aldehyde. But remember, the aldehyde is just kind of a intermediate stage. You can go further. And with a strong oxidizing agent, it does. So you cannot isolate the aldehyde here. It will oxidize up to the corresponding carboxylic acid, and that is what you would isolate. So the point is, with these strong oxidizing agents, if you're using a primary alcohol, yes, it will go to the aldehyde, but then that oxidizes further. There's no way with a strong oxidizing agent to stop at the aldehyde stage. All right, look at this next example. Second example, we're using the Jones reagent. This is that chromium trioxide sulfuric acid combination. But this time we're oxidizing a secondary alcohol. So that's going to oxidize up to the ketone. All right, remember, we talked about this last time. The reason the aldehyde could oxidize further is because it still had a hydrogen which it could lose. With a ketone, however, that carbon has no more hydrogens on it. And so we cannot oxidize this any further. Now let's see an example with the PCC. Remember, the PCC is our weak oxidizing agent. So if we have a primary alcohol like we do in this third example, primary alcohols always oxidize to the aldehyde initially. And here's the difference. With a strong oxidizing agent, as we saw up top, it was impossible to stop at the aldehyde. However, with the weak oxidizing agent, with PCC, you oxidize to the aldehyde and it stops. So that's the real difference. Mm-hmm. It stops. Yeah. Now notice, if you try doing the PCC oxidation on a secondary alcohol, there is really no difference. PCC will oxidize a secondary alcohol to the ketone, but a ketone can't oxidize further, so it stops. So if you do oxidation on a secondary alcohol, it doesn't matter whether you're using a strong oxidizing agent or a weak. Both of these oxidize secondary alcohols to give you the corresponding ketone. The difference is in the behavior of these oxidizing agents when it comes to primary alcohol. Any questions on that? All right. Well, why don't you give me, let's look at these two in the box. Give me the product of this oxidation and then give me the product of this oxidation. Now, the first example is pretty straightforward because you only have one OH group, right? What kind of alcohol is this one? Yep, that is a secondary alcohol. So if we oxidize a secondary alcohol, the oxidizing agent really is irrelevant here because whether you use a strong or a weak, if you're doing a secondary alcohol, you always get the same thing, which is a ketone. Now, this next example is a little bit tricky because we have multiple OH groups. All you have to do is ask yourself, what type of alcohol do you have in each case? What is that alcohol down here? That is a tertiary alcohol. That's easy then, because tertiary alcohols don't oxidize. So I'm just going to put that just as it was. Now, up top, that would be a secondary alcohol. That's also pretty easy because it doesn't matter what kind of oxidizing agent you're using, all secondary alcohols oxidize to ketones. The only one you got to think about are the primary alcohols, which is what you have over here. So what kind of functional group should I put as my product for that one? Yep, that will be the aldehyde because PCC is a weak oxidizing agent. All right, any questions on this? Not PCC, because PCC is the weak one, remember? Any other questions on this? All right, let's go ahead and move on then. Next one is something we've talked about before. We have talked about tosylation before. You'll recall that a tosylate, we introduced this when we were talking about leaving groups. Right, a tosylate, all that is an excellent leaving group. And so I have the formula for tosyl chloride over here. That's largely irrelevant. You don't need to memorize that for this class. Most of the times when people use this, they simply abbreviate it as OTS. Right? But I'll go ahead and show you the mechanism of this at least once. So what this compound is going to do, what the tosyl chloride is going to do, is the oxygen is going to attack it. The alcohol oxygen is going to attack the sulfur of the tosyl chloride, and that's going to cause the chloride to leave. So your intermediate here is going to look like this. And this positively charged intermediate, by the way, is why we have to use this other reagent. The other reagent on the arrow here is called pyridine. And here's the structure of pyridine. Again, you don't need to know that structure for this class. All you really need to know about it is that pyridine is a non-nucleophilic base. And that's its function. Its function in this reaction, and we'll see it used quite a bit going forward, pyridine is going to be used to come in and grab that proton to make a neutral compound. So that is your tosylate. And again, you don't need to know that for me. All you need to know, because usually people, you'll just see this abbreviated as OTS. All you need to know is that OTS is a fantastic leaving group. So I want you to have a look at this example, why we might want to use tosylates. So I've got this alcohol, and I'm going to react it with some sort of an azide ion. Presumably what we're trying to do here is to do an SN2 type reaction and have the azide ion come in and kick out the hydroxyl group. What is the problem with this reaction? This reaction will not work. Why? Yeah. Yeah, I think you're on the right track. So think about if this reaction were to work, think about what the products would be. We would have that carbon chain. The azide would be stuck on there, and we would have lost that. You see the problem? Look at the leaving group. The leaving group is hydroxide. Strong, strong base, terrible, terrible leaving group. This reaction will not work because we have no leaving group. But I could make this reaction work. All I'd have to do is take that alcohol, treat it with tosyl chloride and pyridine. That would give me the tosylate. Well, I've just made a really excellent leaving group. And so now I could add in my nucleophile. And we'd have a reaction. Questions on this one? All right. Tosylates can also be quite useful in elimination. So let's look at remember, we can do dehydration reactions. I could eliminate this OH in acid and heat. Now, could you predict the product of this dehydration reaction? Remember, the acid is just going to protonate the alcohol and it's going to leave. Remember, all dehydrations are E1 mechanism. So you would end up making a carbocation that initially looks like that. What is that going to do? Yeah, this could get to a better carbocation if we did a hydride shift. And so after deprotonation, your major product is that. Because this went through E1, you generate a carbocation, and if it's advantageous, it will rearrange like it did here. Now, the benefit of tosylation tosylates, they don't go by E1 mechanism. Tosylates, you're going to eliminate in base. They eliminate via an E2 mechanism. All right, so I would take my tosylate and I would heat in the presence of pyridine or some other base. Because this is an E2 mechanism, you don't get rearrangement. Questions on this one? Yeah, that's the pyridine. Mhm. Now, there is one final thing we can do with these tosylates. And we just discussed this reagent a minute ago, LAH. We can take tosylates and treat them with lithium aluminum hydride. Now, I want you to, you can, based on what we've already talked about, you can probably imagine what that is going to do. If I take an alcohol, I'm going to first tosylate. And then I'm going to treat it with LAH. Well, remember, LAH is nothing more than a source of hydride. So think about this reaction. We have a good, strong nucleophile, and we have a good leaving group. This is just going to do an SN2 style reaction. H minus is going to come in and kick out the good leaving group. It's a way of deoxygenating the molecule. All right, questions here? Okay, the next transformation is going to be one of the most useful, and you're going to use these all the time. And that is taking an alcohol and converting it to an alkyl halide. Now think about why that would be useful. You know, we've been talking for a while now about the utility of alkyl halides. Turns out they do a lot of chemistry. They are very versatile intermediates. Remember, you can take alkyl halides and do SN2 chemistry with them. You can take alkyl halides and do E2 and eliminate. Recently, we've learned you can take alkyl halides and do the all-important Grignard reaction. Make carbon-carbon bonds with it. So this is something you're going to do a lot. It is certainly one of the reactions you will be carrying on from this semester to the next. So I want to show you a couple of different ways of doing this. First way is just treating the alcohol with HX. Now, primary alcohols, you can do this with, right? And in fact, we did this in lab. You know, we took the in the reaction experiment 11 part A, we took butanol, treated it with sulfuric acid and sodium bromide, right? That made the good leaving group. And then bromide, being a good, strong nucleophile, just came in and kicked it out, SN2. So you can do this with primary alcohols. This is, I'll say, okay. Tell you in a few minutes, there's a much better way of doing this. The yields are not great doing it this way, but it can be done. Like I said, you all did this. All right. With secondary alcohols, this becomes rather tricky because with a secondary alcohol, this is going to go SN1. And it turns out that that process of generating the secondary carbocation is very, very slow. Rearrangements are possible. This is not good. Where this reaction truly shines, though, is with tertiary alkyl halides. Probably see why. The alcohol is going to go out and protonate, just as in the previous examples. This will also go SN1. But because the resulting carbocation is tertiary, number one, it happens quite fast. Number two, there's no possibility of rearrangement. So once you make the carbocation, the bromide just pops in. That is where this reaction truly shines. If you want to take a tertiary alcohol and make a halide, use HBr. It's okay to do this with primary alcohols, but I'm going to show you a better way. Secondary, not good at all. Now, if you want to convert into a chloride, the situation's really dicey on this one. Because if you recall, chloride, if you go back when we were first talking about substitution mechanisms. I gave you that listing of nucleophile strength. Chloride was listed as a quote unquote fair nucleophile. So this reaction of alcohols with HCl becomes really slow. And in fact, it's so slow, they will usually add this zinc chloride to it. Zinc chloride is a Lewis acid, and this combination of HCl with zinc chloride is called the Lucas reagent. And that zinc chloride just kind of helps make the OH a better leaving group. All right. But again, I'm really only showing you this because sometimes this questions about the Lucas reagent shows up on standardized tests. Nobody really does that very much anymore. The Lucas used to be used as a test for primary, secondary, or tertiary alcohol. So if you had a solution, you had some alcohol, you didn't know what it was, you can use this Lucas test to figure out whether you were dealing with a primary, secondary, or tertiary alcohol. And the way you could do that is, so let's say you had 3 test tubes. One had a primary, one had a secondary, one had a tertiary alcohol in it. The way you would do this test is you would have the Lucas reagent, HCl zinc chloride, and you'd add a little to each of the test tubes, and then you'd shake them up. Well, if the reaction occurs, you're making a chloroalkane. Well, chloroalkanes are not soluble in aqueous solutions that the Lucas reagent is. And so as the alcohol got transformed into the chloroalkane, you would see 2 layers develop. And because this is going through SN1 chemistry, this happens very, very fast. Within seconds for tertiary. All right, so you add a little bit of the Lucas reagent to each one, shake it, and then within seconds, if you see 2 layers, you know it's a tertiary alcohol. Occurs a little bit slower for secondary. Again, secondary carbocation is a lot less stable than a tertiary. So this process is going to happen slower. It'll happen within minutes. And for a primary, you get no reaction whatsoever. So this used to be used as a test for alcohol. But again, it's pretty old school chemistry. If I want to know what kind of alcohol I'm dealing with, if I have a mystery alcohol, all I would really need to do is go put it in the NMR. We don't really need all of these little chemical tests anymore because we have spectroscopy. But in the days before instruments, that's all chemists had to rely on were these little creative chemical tests that gave you visual clues. Okay, so I've shown you kind of the old school way. I want to show you the better way. If you want to make an alkyl halide, a bromide specifically from primary and secondary alcohols, use PBr3, phosphorus tribromide. So the way this reaction works, I'll kind of just show you a little baby mechanism. If you treat this with PBr3, the alcohol is going to attack the phosphorus, and that's going to kick out one of the bromides. So you're going to end up making this. Right? Notice you've got PBr2 stuck on the oxygen because we kicked out a bromide as the oxygen attacked. Now this is where the pyridine comes in. The pyridine is going to come in and grab that proton, just like we saw with the tosylation. And this whole thing is going to become effectively a leaving group, the fancy leaving group. That bromide that we kicked out is going to come in and attack and kick that leaving group out. Resulting in the halogenation. So I guess what I would say the take-home message in all of this is if you want to take a primary or secondary alcohol to the bromide, use PBr3. If you want to do a tertiary, use HBr. And again, the reason for this is the mechanism of this PBr3 is an SN2. So you can use PBr3 on primary and secondary alcohols. Because this is an SN2 reaction, you cannot do this with tertiary alcohol. For chlorination, there's also a better way of doing this. For chlorination, we're going to use something that's called SOCl2 or thionyl chloride. Thionyl chloride looks like that. And this mechanism is going to be very, very similar to the one we just saw. The oxygen attacks the sulfur, and that kicks out a chloride. The pyridine, as we've seen, is just going to act as base. And just like we saw with the PBr3 mechanism, this whole thing is just a big fancy leaving group. And so the chloride that we ended up kicking out is just going to come in and attack and cause that group to leave, resulting in the chlorination. Now, kind of an interesting fact about this reaction is that that SO2Cl breaks down to that. And for those of you that are unfamiliar with sulfur dioxide, it's a gas and it is disgusting. It is a very, very thick smelling gas and it has a very strong smell of rotten eggs. And so as you do, we used to have you do this reaction in Chem 421 and having everyone do this reaction generating SO2. The lab did not smell very good, let's just say that. But we don't really do that anymore. It turns out that the thionyl chloride became quite difficult to get. Um, it's on a list, and so you could only get it in small quantities because I think you could use it to make illicit substances and explosives. So it became very tightly regulated and kind of expensive to get. And so we just kind of found alternate ways of doing that reaction. But so just like before, the bottom line, the take home message here is if you want to take a primary and secondary alcohol and make it a chloride, use thionyl chloride. Right? So I guess to summarize this part of the discussion, if you have primary or secondary alcohols, use either PBr3 if you want to make the bromide or thionyl chloride if you want to make the chloride. If you have a tertiary alcohol, use HBr or HCl. That's the take home message. All right, so I want you to work on this. Start getting some practice and kind of putting these things together. So this is kind of like a reaction map. So see what you can do with this. Take a couple minutes and work on this. So hopefully these first two or three steps are pretty straightforward for you. Stuff we've been doing for a while now. What are we doing in that first step of this sequence? Taking the alkane and treating it with Br2 and light. Uh-huh. Well, you're given the reactant. So Br2 light, that is, of course, just photohalogenation. We've been doing that for a couple months now. And that's going to put the bromine, of course, at the most substituted position. Then in the second step, we're treating the halide with strong base. That is a tertiary halide, so that will eliminate E2. And the E2 will go to the Zaitsev product because we're using just a regular strong base. Then we are taking that alkene and treating it with borane and basic peroxide. So that is a hydration reaction, more specifically, the anti-Markovnikov hydration. So that's going to put the OH at the less substituted position. Oh, this next step's a new one. What is this going to do to our newly formed alcohol? It's going to make the bromide. And then what is that last step? Taking the bromide and treating it with this laundry list of things. What is that going to do? What kind of reaction is that? That is the Grignard. And so remember, what that does in a reactivity sense is it basically just makes that carbanion. It makes the negative charge where the halide was. And then that nucleophile will come in and attack the carbonyl. Okay. Can you give the product of that? So this would be the initial product, right? You always get that alkoxide initially, which is why you always need one more step where you acidify to give that O minus its proton back. So once you acidify, we would make that. And this is in line with what we discussed last time. We talked a lot about the Grignard reaction last time. And what did we say? We said that if you add a Grignard reagent to a regular aldehyde, you should be making a secondary alcohol. And in fact, that's what we've got. All right, questions on that? Okay. I think I want to introduce you to one more reaction and then we'll call it quits for today. So we've been talking about this for quite some time. This is simply the dehydration of an alcohol. So that's really old news, right? As an example, um, if I had this alcohol and I treated it with phosphoric acid and heat, remember how this would work. The oxygen is going to go and protonate. That makes the good leaving group. Remember, dehydrations are E1, so it would just leave. What do you think happens from here? Yeah, if this were to do a methyl shift, we'd get a better carbocation, right? And then when the deprotonation occurred, that would be the major product. So again, nothing new there. An E1 mechanism, rearrangement possible. The last reaction I want to look at together is another type of dehydration, but this one is not accompanied by rearrangement. And you can do that through the use of this reagent. This is known as phosphorus oxychloride, POCl3. I'll show you on the exact same alcohol we just looked at. So phosphorus oxychloride looks like this. And so this is going to look a lot like those other phosphorus reactions, the PBr3, the thionyl chloride reaction, in that the oxygen is going to go out and attack the phosphorus, and that's going to kick out one of the chlorides. Well, there's that positive oxygen species that we've seen multiple times now. That's why we have the pyridine present. And then the pyridine is also going to come in the next part of this and grab that adjacent proton and kick that out. Notice this is done in base. This is an E2 mechanism, and therefore no rearrangement. All right. Any questions on this? All right. So I think that's probably a good place to stop for today.